Hello, Chemistry 12. This is Mr. Chan. And today what we're going to do is we're going to go over the second part of your hydrolysis notes. Now, this is a continuation of the notes from last day. And remember when we talked about hydrolysis, we focused on the idea that the substance or the ion had to be at equilibrium. Okay, you notice here, I said NH4 in this example was on the left side at equilibrium. For this example, for the Cn-1, it's the right side at equilibrium. And in this example, the CO3, a right side at equilibrium. Now, you notice the commonality with all three of these is the fact that they are at equilibrium. So the question is, why do the parts from a weak acid, weak base, be able to hydrolyze? And that's because the substance exists as equilibrium in water. As a result, the conjugate acid base has the ability to react itself. Now, for example, let's say we had HCN versus HCl. Now, for HCN, it is in equilibrium with H plus and Cn minus 1 versus HCl, which is H plus and Cl minus 1. Now, if you take a look, notice this is complete dissociation. So in this case, because HCl is complete dissociation, Cl minus 1 is too weak to react. It cannot push the reaction back to the left. Now, versus here, where you have an equilibrium system, what happens is the Cn minus 1 is able to react enough to push the equilibrium back. Equilibrium that way. All right, and that's the key thing because the HCl is a strong acid, so it dissociates completely. So the Cl minus 1 or the conjugate base is too weak to react. But if it exists as equilibrium, there is enough of the conjugate base in this example to push the equilibrium back towards the reactants. Okay, now in the previous example, we've always only had one salt that would react. So in this example here, we had the negative ion, fluorine ion minus 1. Here we had the negative ion. Here we had the negative ion. And here we had the positive ion. Now, but what about in this particular case? What if both the anion and the negative and cation undergo hydrolysis? To determine if the salt will produce an acidic or basic solution, one needs to compare the Ka and Kb values. Now, what do I mean by this? So let's say NH4, NO2, both of these will hydrolyze. So both at equilibrium. So since they're both at equilibrium, therefore, it would hydrolysis. So now what we do is we take a look, again, location. So we have NH4 plus water would be in equilibrium with NH3 and H3O plus. And the other reaction, I'll put that in a different color, is we have NO2 minus 1 and water. And so what we have is we have HNO2 and OH minus 1. Now, in this case, because both of them work, what we have is NH4, because we produce H3O plus, we have a Ka value. And for NO2, we would have a Kb value. And so what we would need to do is we have to determine our Ka and Kb. And what we have to do is we have to compare. And whichever one is bigger would be the dominant reaction. Okay? Now, some ions undergo hydrolysis contain acid hydrogens and may undergo two possible reactions. And like the previous example, one needs to compare Ka and Kb values. Now, for example, HCO3 minus 1, is it acidic or basic solution? Now, in this particular scenario, if you take a look at HCO3, you will notice that it can either act as a base, which is here on the right-hand side, or it can act as an acid. So which one would it prefer to do? So in this particular scenario, we have to treat it as either an acid or a base. So in this case, we have HCO3 plus water would give you H3O plus and CO3 minus 2. And so what we have is we have our Ka expression. So Ka is equal to concentration of H3O plus, concentration of CO3 minus 2, all over concentration of HCO3 minus 1. And we have our base. We have our Kb is equal to, in this case, it would be Kw over Ka of our conjugate acid, which is H2CO3. Okay, and that is equal to concentration of H2CO3, concentration of OH minus 1, all over concentration of HCO3 minus 1. And again, what we need to do is we need to compare the two to see which one is larger, and that would be the dominant reaction. Now, the one thing when you're calculating Kb is, remember, it's Kw over Ka of the conjugate acid. So that's why I'm highlighting the fact that you have to be aware it's H2CO3. All right. Now, there are some special ions to consider for hydrolysis: aluminum, chromium, and iron. If you take a look on your acid-base chart, you will notice that you have chromium, you have aluminum, and you have iron here. Now, it has been experimentally determined that these ions produce an acidic solution. But the question is, how do they do that? How is iron, which has no hydrogen in it, how is it able to produce an acidic solution? Well, chemists theorized this, that what happens is these ions, aluminum, chromium, and iron, what happens is they form this complex, this hexaaquo ion. Hexa means 6, aquo means water. So 6 waters attached. And so what happens is now this new complex is then able to donate the proton to another water. And what you get is you get your H3O plus. Okay, so that is something that chemists have sort of deduced or hypothesized, given the fact that iron and aluminum and chromium solutions are acidic. Now, another thing that we want to talk about is something called acidic anhydride. So what is an acidic anhydride? Is an oxygen-containing compound that combines with water to produce an acidic solution. Now, it is generally a covalent compound. Now, what do I mean by this? The most common example would be CO2. carbon dioxide. Now, what happens is when carbon dioxide reacts with water, what it will do is react with water to form carbonic acid, H2CO3. So this is carbonic acid. So this is called an acidic anhydride. So what happens is a neutral covalent compound that contains oxygen can react with water to produce a weak acid. And this is why if you were to collect rainwater, what's happening is it is slightly acidic. Now, some of you might say, well, who cares? And this is what's happening with global warming. With global warming, what's happening is more carbon dioxide is being released into the atmosphere. Not all of it is being used up by the plants. A lot of it is being absorbed in the oceans, like the Pacific Ocean, Atlantic Ocean. And what they're finding is that as more carbon dioxide is in the air, the oceans are actually getting more acidic because more carbon dioxide is being dissolved. And what's happening is you're forming more carbonic acid. And so what that's doing is slowly eating away at things like the coral reefs, is slowly eating away at the shells of things like oysters or lobsters or crabs. And what's happening is that it's actually weakening those shells and making those crustaceans more vulnerable to, environmental crashes or, being crashed against the rocks. The shells used to protect them, but now they're finding that they're getting more and more injured. So that's why, when we have increased carbon dioxide, what happens is that the oceans are starting to get a little bit more acidic, and that's affecting a lot of the marine life. The opposite side of acidic anhydrides is basic anhydrides. It's an oxygen-containing compound that combines with water, in this case, to form a basic solution. Generally, it's an ionic compound. Okay, now, for example, let's say we had Na2O, sodium oxide. Now, in this case, sodium oxide is an ionic solid. So what happens is the first step for an ionic solid is that it dissociates. So what happens is the Na2O breaks apart to 2 Na plus and O minus 2. And what happens is, you recall the sodium, this is a spectator. But what happens is the O2 undergoes hydrolysis, see? And what you get is you get 2OH minus 1. This is your base solution. Okay, so that is a basic anhydride. So not only can ions react with water to produce acidic and basic solutions, like what we had talked about before, but neutral substances, whether it's covalent compounds or ionic compounds, can also produce an acidic or basic solution. And these are what we call anhydrides. So neutral molecules that contain oxygen that can either produce an acidic solution like CO2 or a basic solution like Na2O, an ionic solid. All right, folks, that is it for today. Thank you very much. Have a good day. Bye-bye.